Okay, so let's just go ahead and jump into examples. So we have a 2x2 matrix, okay? Let's determine the eigenvalues and the eigenvectors that are going to be associated with this 2x2 matrix. Okay, so the first step, we're going to look for the eigenvalues. So we're going to take the determinant, okay? Now this is going to be A minus lambda I, okay? And that's going to become the determinant All right, so that's 4 minus lambda, that's going to be 1, and that's going to be 6, and this is going to be 3 minus lambda. Okay. So the minus lambdas just go in the diagonal, because when you multiply lambda times the identity matrix, the identity matrix just has 1 in the diagonal, so your lambdas only end up going in the diagonals. Okay? So now we're going to take the determinant of this guy right here. That's going to equal, this is going to be 4 minus lambda times 3 minus lambda, and then minus 6. Okay? So, 3 times 4 is just 12. All right? And then we'll have negative 3 lambda and a negative 4 lambda, which would be a minus 7 lambda. And then plus lambda squared, and then minus 6. Okay. So let's reorder this so that it's nicer to deal with. So what are we going to get? Lambda squared, and then minus 7 lambda, and plus 6. Okay. Now we're going to factor this one. So, how could I factor that? Let's say, what do I take first? All right, lambda minus 1 times lambda minus 6. And we're going to set that equal to 0. All right? So, lambda 1 is going to equal 1, and lambda 2 is going to equal 6. Okay, so step 1 is complete. We have found our eigenvalues. All right, now what we're going to do is we're going to find our eigenvectors. Okay. All right, so, all right, what we're going to do is we're going to solve for V1, okay? And so this is going to be A minus lambda 1I, V1 is going to equal 0. Okay? So my lambda 1 is 1. Okay. So that becomes 4 minus 1. This is 1, this is 6, and this is 3 minus 1. So 3 minus 1, 4 minus 1 is 3, that's 1, that's 6, that's 2. Now if I take the top row and I multiply by negative 2 and then add it to the bottom row, you'll see that the bottom row completely disappears. Alright, so we have 3, 1, 0, 0. Okay, so we ended up with a pivot and a free variable. So like always before, I want 1 where the pivots are. So what I'm going to do right there is I'm going to divide by 3. That's 1, 1/3, 0, and 0. Okay, and so now we want to think about this problem as, what could I pick as V1 that would come out with 0 and 0? That's the question. remember that when we were looking for null spaces, said, okay, this is the free variable right here, this is the pivot. What does this thing eventually come out to? This means that x1 plus 1/3 x2 equals 0. Or that x1 equals negative 1/3 x2, because we're setting this equal to 0, so we'd have to move it to the other side of the problem. So v1 would be negative 1/3 and 1. Okay. Now, let's ask ourselves the question if we got this answer right. So if we have A minus, or A acting upon V1, it should equal lambda 1 times V1. Now, this is a specific case where lambda 1 equals 1. So A acting upon V1 will just produce V1. So let's double check that. Okay. So 4, 1, 6, 3. Now this is going to act upon okay, so think about what happens when 4, 1 acts upon this guy. When 4, 1 acts upon it, I'm going to get negative 4/3 from the top one and 1 from the bottom. So negative 4/3 and 3 over 3. So it's negative 1 over 3. Okay? Now 6, 3 acting upon negative 1/3, 1. So 6 acting upon the negative 1/3 is going to be negative 2. And then negative 2 plus 3 is 1. So, yeah. Okay. And this is just because our lambda 1 is 1. Okay. So, now that we solve for V1, we're going to solve for V2. Set that equal to 0. Okay, so my lambda 2 is 6, all right? So this becomes now 4 minus 6, 1, 6, 3 minus 6. All right? So 4 minus 6 would be negative 2, 1, 6, and negative 3. Okay. This is happening again just like on the previous problem. Where if I take that top row, and if I multiply it by 3 and add it to the row below it, it's going to completely kill off the row. Why? Because when we take the determinant and set it equal to 0, what are we doing? We're getting linearly dependent vectors. And so a free variable does exist in this problem. So if I eliminate the entire bottom row, I'm going to end up with negative 2, 1, 0, 0. Okay? All right, and once again, I like my pivots to be 1. So I'm going to turn that into a 1. And so that becomes 1 and negative 1/2, 0 and 0. Okay. Now this is going to act upon V2. And this is going to equal 0, 2. Okay? All right. Now think about this, if we were talking about this as being a free variable, let's say x2. So this is saying x1 minus 1/2 x2 equals 0. Or that x1 equals 1/2 x2. So if x1 equals 1/2 x2, that means that V2 would be 1/2 and 1. Okay. Now let's check our answer. Okay, so if we have the matrix A act upon this vector, v2, okay? What's it gonna do? It's gonna spit out lambda 2 v2, or it's gonna spit out 1/2 1 multiplied by 6, okay? So let's check and see if that really happens. So we have 4, 1, 6, 3. Now acting upon 1/2 and 1. Okay. All right. Now 4, 1 acting upon this guy. What's that going to really be? 4 times 1/2 is 2. All right, and then 2 plus 1 is 3. Okay. All right. Now this one acting upon 6 acting upon 1/2, that would be 3. And then 3 acting upon 1 is also 3, so 3 plus 3 is 6. Okay? So that does equal 6. Times 1/2, 1. Okay, so we really know that we did get our second eigenvector, v2, which is 1/2, 1. Okay, so we got lambda 1 is 1, lambda 2 is 6. V1 is negative 1/3 1, and V2 is 1/2 1. So those are the eigenvalues and eigenvectors that are associated with the matrix 4, 1, 6, 3. Always multiplied by a scalar if possible.